Okay, this is 11C, continuing our introduction to predicate and quantifier logic. In this video, the last of this unit, I'm going to talk about the basic interpretations of variables and quantifiers in the logical language, given that we've talked a little bit about the interpretation of quantifiers and a little bit about how pronouns work. So we'll start by looking at atomic formulas with free variables. We're going to let F symbolize as a frog and G symbolize as green. So Fx, well, then it's true if x refers to a frog, it's false if x refers to a non-frog, and this has no truth value if x doesn't refer. So just like it is tall, fx gets a truth value only given an assignment of an object to x for x to refer to. Similarly, gx is true if x refers to a green thing, false if x refers to a non-green thing, and it has no truth value if x doesn't refer to anything at all. Complex formulas with free variables can be understood similarly, so if we have fx and gx, then we can say that this is true if x's referent is both a frog and green, i.e. it's a green frog. It's false if x's referent either isn't a frog or isn't green, and it has no truth value if x doesn't have a referent. If fx then gx, this is true if x's referent isn't a frog, and so the antecedent is false, or is green, and so the consequent is true. We can also say it's true if x is like this. If x is the frog, then x is green, but that might not be totally perspicuous, and so this is another way of saying that. It's true if either the referent of x is not a frog or is green, because a conditional is true if either the antecedent is false or the consequent is true. This is false if x's referent both is a frog and is not green. The conditional is false if it has a true antecedent and false consequent, and what would that mean? That would mean that f was true whatever x referred to, and g was false of whatever x referred to, so x was a frog but was not green. So quantifier-free formulas with variables are like quantifier-free sentences with pronouns. The quantifier-free formula with a variable in it by itself is not true or false. It does, however, specify a property like being tall, or being tall and green, or being a frog and green, being such that green if a frog, or said differently, either not a frog or green. And then if we assign an object to the variable, then we can say that the formula is true if and only if that object has the property. And so they're basically working just like how pronouns and sentences do. So how do quantifiers get involved? Well, just as we can ask, is fx true when we assign this to x, we can also ask, is fx true when we assign, is there at least one object that when we assign it to x, fx is true? And we can have a sentence that says that the answer to that is yes, and that sentence is some x fx. This is true if there's some object that when it's assigned to x makes fx true, and so there's a frog, right? Because that's what you have to be like if when you're assigned to x you make fx true. Given how we're interpreting f as meaning frog, we could interpret it as meaning something else, but given that it means is a frog, then that's how it works. Some x fx is false if each object, if assigned to x, makes fx false. So in other words, each object is not a frog. So this is true if and only if there is a frog. So again, there's the condition that the formula is true of at least one object when it's assigned to the variable, but we have multiple occurrences of the variable in question. So we have some x, fx, and gx. So this is true if there's some object that when assigned to x makes fx and gx true. And what does x have to be like to do that? It has to be a green frog. On the other hand, this is false if every object when assigned to x makes fx and gx false. And how does it do that? Well, either it's not green or it's not a frog, so in any case it's not a green frog. And so some x, fx, and gx says there is a green frog, because it's true when there is at least one thing that when assigned to x makes fx and gx true, and so one thing that is a green frog, and it's false if there are no such things. If each thing when we assign it to x makes fx and gx false, and so it's not a green frog. So some x, fx, and gx said some frog is green. Rules. A variable can refer to a particular object, or on different occasions, different objects. And then the truth value of a quantified sentence depends upon what happens when different objects are assigned to the variables in the sentence. So they, on their own, don't refer to anything, but can be assigned particular objects, and when they are assigned a particular object, the sentence gets a truth, or the formula gets a truth value. And then if you have a quantifier in front, then the truth of the quantified sentence depends upon what happens when you assign objects to the variables in the unquantified sentence. This is a slightly rough description. We'll get a somewhat more precise description of exactly the way in which quantifiers and variables interact, but for now it's good enough. So, to finish this off, some simple symbolization. So we say some frog is green. Well, this is true if and only if something is such that it is a frog and it is green. And how do we, so in other words, if and only if the conjunction fx and gx is true of at least one thing, if and only if some x, fx, and gx. So this is a symbolization of some frog is green, and that's what we want. Some frog is green is symbolized as some x, fx, and gx. And note that it's some x, fx, and gx, and not, for example, some x, fx, and some x, gx. That would say something is a frog and something is green, but it wouldn't tell us that it's the same thing that's both green and a frog. What about every frog is green? Well, this is tricky. You might think it's some x, fx, and gx, but think about what that says. That says everything is such that, or each thing is such that fx and gx is true. So what does that mean? It means that fx and gx is true of me, and fx and gx is true of you, and fx and gx is true of this mouse, and of this keyboard, and so on. And fx and gx is true of none of those. Why? Well, because I'm neither a frog nor green, and you're neither a frog, and I assume not green, and the mouse is not a frog, and it's not green, and the keyboard is not a frog, and it's not green. So, on the one hand, we could say, is it true that every frog is green? Well, no, but it could be true, and it doesn't matter what color I am, or you are, or the mouse and the keyboard, because they're not frogs. Some x, fx, and gx says everything is a frog and green, which is not what every frog is green says. Every frog is green says, look at the frogs. If they're all green, true, otherwise false. But it doesn't care about the non-frogs, whereas some x and fx and gx says everything is a frog, and that's not what every frog is green says. So what does every frog is green say? Well, you could read it like this, and we'll talk about whether or not this is the best way to read it, but one way would be, each thing is as follows. Either it isn't a frog, or it is green. That is, if it is a frog, it's green. And think about it, right? We don't worry about the things that aren't frogs, so they're fine. There are two things that sort of, you look at a thing, you need to know, if it's not a frog, you think no problem. If it is a frog, you have to find out, is it green or is it not? And if it is, you're good to go. So we could think of every frog as green as saying each thing is such that if it's a frog, it's green. And so that would be saying if fx then gx is true of each thing, and that is for all x, if fx then gx. So we want to say every frog is green is symbolized as for all x, if fx then gx. And again, it's not if for all x, fx, then for all x, gx. We have one quantifier that has scope over all of if fx then gx. So this is what you need to know to do the homework for next week. I'm going to go ahead and do a short video on just using the symbolization module to enter in symbolizations of this kind, and then you'll get to do a few. But in terms of the content, this is all you need to know. So you're good to go. If you have any questions, please let me know.